I am Shamsunisa from Royal Degree College, Chemistry Department. As we have already started Unit 3rd, Physical Chemistry, our chapter name is Chemical Kinetics. In this, today we are going to study about order of reaction, classification of reactions in terms of order, first order reaction, characteristics of first order reactions, and problems based on first order reaction. So we'll see first order of reaction. What is order of reaction? Sum of powers of the concentration of reactants in the rate law is termed as order of reaction. In a reaction, see the reaction here, A plus 2B. These two are the reactants. They are reacting, and as a result of that we are getting the product C plus D. So one molecule of A reacts with two molecules of B to give products. So number of molecules of same or different reactants involved in the reaction is called molecularity. So here in this reaction you can see one molecule of A, it is reacting with the two molecules of B. So how many molecules are taking part in the reaction here? 3, isn't it? So the molecularity of the reaction is 3. Let the rate law of above reaction is determined experimentally. Rate, it is equal to K, that is constant, molar concentration of A to the power X into molar concentration of B to the power Y. From first law, order of reaction with respect to A is X and the order of reaction with respect to B is Y. So overall order of reaction is we are adding these two parts, that is X plus Y. So we'll get the order of reaction. Now we'll see about the classification of reactions in terms of order. If rate of reaction is proportional to the first power of concentration of reactant A, the reaction is called first order with respect to A. Here you can see the reaction R, it is equal to K, molar concentration of A. So the next is R, it is equal to K, molar concentration of A to the power 2. Here in power, the 2 is there, isn't it? So that's why the order of the reaction is second. That is second order reaction. Next, R, it is equal to K, molar concentration of A into molar concentration of B. Here, molar concentration of A, nothing is there in the power. It means that 1. Okay. Then molar concentration of B, it is also 1. So 1 plus 1, we are adding the parts. So we get the order of reaction, that is second order reaction this one. So the reaction is first order with respect to A here, and the reaction is of second order with respect to A and B, isn't it? And with respect to B, if we'll see, the reaction is of first order. R, it is equal to K, molar concentration of A to the power 3. Here the power is 3, isn't it? So the reaction is of third order. The order of reaction always need not be a whole number, that is, it can be fractional as well as 0. In some heterogeneous or surface reactions, the rate of reaction is independent of the concentration of the reactant. Means it will not depend on the concentration of the reactant. Such reactions are said to be of 0 order. Example here you can see, we are taking hydrogen H2, it is reacting with chlorine Cl2. The reaction will take place in the presence of light, that is Hb, and we are getting the product as 2HCl. This reaction is of 0 order reaction. Here the decomposition of hydrogen iodide in the decomposition of ammonia, phosphine were on gold and tungsten metal surfaces. So as a result of that, here we will get the 0 order reaction. The order of a reaction should be determined experimentally but not from the chemical equation. Here you can see the example. See the reaction 2N2O, it will give 2 molecules of nitrogen and 1 molecule of oxygen. From the chemical reaction or chemical equation, it looks like a second order, but actually it is found to be first order reaction. That is, rate of the reaction, it is equal to K molar concentration of N2O. So the above reaction takes place actually in two steps. The first step is N2O. It is undergoing the slow reaction, and as a result of that we are getting nitrogen plus nascent oxygen. Next step is we are taking the 2 moles of nascent oxygen. The reaction will take place fast, and as a result of that we are getting O2, that is oxygen molecule. So the rate of reaction is always governed by slow step. Therefore, this reaction is of first order reaction. Next we will see about first order reaction. Reactions whose rate is determined by the change of only one concentration terms are known as first order reaction. Consider a reaction. Here you can see a reaction, that is A is the reactant. It will give the products. At the time 0, initial time, concentration of capital A is small a and concentration of the product is 0. But at the time t, concentration of the product is x and concentration of the reactant A is A minus x. Initially concentration of the reactant is A and x moles product formed after the time t. The first order rate equation for the above reaction can be written as, like this we are going to write dx by dt, that is differentiation of x with respect to time. It is equal to K1, that is rate constant for the first order reaction, molar concentration of capital A to the power 1. In the next step, dx by dt, it is equal to K1. In place of molar concentration of A, we are writing the value of A after the time t. How much? A minus x. So, we are bringing this A minus x to the other side of equal to. So, we are writing here dx by A minus x. And this dt we are bringing that side. So, we are getting here it is equal to K1 dt. Integrating on both sides. Like this we are writing. See, integrating on both sides we are using this formula for integration. That is integration of 1 by x into dx. It is equal to minus ln x. So here we are writing like this, integration of 1 by a minus x. 1 by x. X is here x is a minus x into dx. It is equal to K1. It is constant, na? So we are writing K1 as it is. Then integration of dt. See here, integration of dx, it is equal to x. So integration of dt, it is equal to t. Like this here, integration of 1 by a minus x into dx, it is equal to what? Minus ln a minus x. Okay. It is equal to K1 integration of dt is t plus I we are writing. I is nothing but integration constant. It is our equation number 1. At time t equal to 0 and x equal to 0. We are substituting these values in this particular equation. Okay, in the above equation, first equation. Minus ln, then a minus x. X is what? 0. So a minus 0 is a. We are writing it. Then it is equal to K1 into t. What is t? T is 0. So K1 into 0 is 0 plus I as it is we are writing. Or we can write in this way, I it is equal to minus ln A. Substituting the value of I in equation 1. Already you have seen the equation 1, isn't it? In place of I, here we are substituting the value of I. Equation 1 we are writing here minus ln A minus x, it is equal to K1 t K1t here the value is plus I, okay, in our equation 1. So in place of plus I, we are writing the value of I value is minus ln A. Now this minus ln A we are bringing to the other side, so it will become plus ln A, then minus this value as it is we are keeping, minus ln A minus x, it is equal to K1t. Then look at this here, we are using this formula, that is ln A minus ln B, it is equal to ln A by B. Okay, so ln, we are writing C here, ln A minus ln A minus x, it is nothing but it is equal to ln A by A minus x. It is equal to K1t. Now look at this, we are using this formula now. ln A, it is equal to 2.303 log A. Okay, so in place of ln, we are writing the value as 2.303 log A by A minus x, it is equal to K1t. Now what we are doing, this t we are bringing to the other side, 2.303 divided by t, then log this value as it is we are keeping, log A by A minus x, it is equal to K1. Or we can write in this way, K1 it is equal to 2.303 by t log A by A minus x. This is the rate equation for first order reaction. Above equation can also be written as K1 it is equal to 2.303 by t log C naught by C, where C naught or C0 it is equal to what? Initial concentration of reactant. C is nothing but concentration of the reactant after time t, and K1 is first order rate constant. Now we'll study about characteristics of first order reactions. The first one is units of first order rate constant. K, as we know that the formula is, the first order reaction equation or the formula will be like this, K it is equal to 2.303 by T into log A by A minus X. Okay. Now we are writing the units. K it is equal to 2.303 log, okay, into A value. Unit of A is moles per liter divided by unit of A minus X is moles per liter. So the K it is equal to moles per liter gets cancelled. So we'll get the K it is equal to time inverse. If time is expressed in seconds, units of first order rate constant is second inverse. Next we'll see about half-life period of a first order reaction, that is T-half. The time taken for the concentration of the reactants reduced to half of its initial value is called half-life period. For the first order reaction, when T is equal to T half and X is equal to A by 2. Look at this very carefully. This formula we are using for the first order reaction. K it is equal to 2.303 by T into log A by A minus X. Okay. So in the next step, K it is equal to 2.303 as it is we are writing, divided by T is there na, in place of T we are writing the value of T. What is the value of T? T half that we are writing into log A by A minus X as it is. Then we are bringing this T half to the other side. Okay, so we are writing here T half it is equal to this K we are bringing to this side, so it will go to the denominator, 2.303 by K into log A by A minus X. Next is T half it is equal to 2.303 by K as it is we are writing into log A by A minus X is there na, in place of X we are writing the value of X. What is the value of X? A by 2 that we are writing. Now T half it is equal to 2.303 by K into log A by A minus A by 2 is there na, A minus, so A nothing is there in the denominator of A, so it is in understanding we can say that it will be 1. So we are writing here A by 1 minus A by 2. Now we are taking LCM, girls. See here, 2 into A what you will get? 2a, isn't it? 1 into this a, you will get a. So like this we are writing in the next step, this part. Look at this part. 2a minus a, it will be equal to what? A. 2a minus a is a divided by 2, so we are writing a by 2. Each means everything here as it is. In the next step, this t of it is equal to 2.303 by k into log a by 2, isn't it? So this a by 2 is there now, it is becoming reciprocal. So we'll get like this, a by a into 2 this side. So a gets cancelled. So what you will get? Log 2, isn't it? Then the value of log 2 is 0.301. Okay, 0.301. Now we are multiplying these both values, that is 2.303 into 0.301. So we will get 0.693 by k. That is t of it is equal to what? 0.693 by k. From the above equation, it can be known that half-life period, that is t half for first order reaction, is independent of initial concentration of the reactant. Next is graph evaluation of K1. As we know the formula like this of the first order reaction, that is K1, it is equal to 2.303 by T into log A by A minus X. Okay. So here what we are doing, this particular what, that is log A by A minus X, we are bringing to the other side. Okay. It will be equal to this K1 we are bringing to the another side. So we are writing like this, K1 by 2.303 into T, like this. Once again, listen this part very carefully. See, this K1 is there now. This T we are bringing to the other side. Okay. So it will become what? K1 into T. Then divided by this 2.303 will go that side. So it will come in the denominator. So K1 into T by 2.303. That will be equal to which value? This value, isn't it? Log A by A minus X. Now we are using this particular formula. Log A by B, it is equal to log A minus log B. So log A by A minus X, it will be equal to what? Log A minus log A minus X. It is equal to this value as it is we are writing, K1 into T by 2.303. Now log A we are keeping as it is. Log A, this value we are keeping as it is. This one, K1 into T by 2.303 we are bringing to the other side. So it will become negative. Minus K1 into T by 2.303. That will be equal to this value, girls. Minus log A minus X is there. Now from that side we are bringing to this side. So it will become a positive. So log A minus X. Next is graph from first order reaction. Here you can see the graph. Log A by A minus X is plotted against the time interval T. Then a straight line is passing through origin is obtained. Here the slope it is equal to K1 by 2.303. Next you can see this graph here. Log A minus X is plotted against the time interval T. We get straight line with intercept log A. With intercept log A. So here slope is negative, which is equal to minus K1 by 2.303. Now we will see the problem, girls. The first problem is first order reaction is 20% completed in 20 minutes. Calculate rate constant and formula. Here we'll see the solution. First order rate equation is K1 it is equal to 2.303 by T into log A by A minus X. Now the given data is A is equal to 100, X equal to 20 and T equal to 20 minutes. We are substituting these values in this formula. K it is equal to our equation is what our formula is 2.303 by t log a by a minus x. Okay. Now in place of t, we are writing its value as 20. In place of a, we are writing 100. In place of x, we are writing 20. Now 100 minus 20, you will get 80. 100 by 80. 0, 0 gets cancelled. 2 4s are 8, 2 5s are 10. So you will get the value as 5 by 4. Okay. Now if we are dividing this value, we will get log 1.25. Next step is k is equal to 2.303 by 20 into log value. That is log value of whom? 1.25. So we'll get the log value is 0.097. Now, first of all, we are dividing this. That is 2.303 by 20. So you will get the value 0.11515. It should be multiplied with this value 0.097. So if we are multiplying these both values, we are getting the k value as 0.01117 per minute. Now the half-life of the first order reaction T half, we know that its formula is it is equal to 0.693 by k. Now in place of k, we are writing the value of k. What the value of k we got here? 0.01117. So we are dividing this and we will get the value as 62.041 minute. That is the half-life period of the first order reaction. Now we'll see the second problem. The rate constant for a certain first order reaction is 1 into 10 to the power minus 5 per second. Calculate the time taken for 20% completion of reaction. Given data is here, k is equal to 1 into 10 to the power minus 5 per second. A value is 100 and x value is 20. We are using this formula for the first order. K is equal to 2.303 by t into log a by a minus x. Now we are rearranging this equation. Why? Because we don't know the value of t. So we are bringing t to the other side. The k will go to the denominator. Okay. So t, it will be equal to 2.303 by k into log a by a minus x. Now in place of k, we are writing the value of k. The value of k is 1 into 10 to the power minus 5. And a is 100. And x is 20. That we are writing. Then in the next step, we are substituting the value 100 minus 20. What you will get? 80. Okay. And then in the denominator, here you can see. Look at this once again. 2.303 divided by 1 into 10 to the power minus 5 is there. Na? This value 10 to the power minus 5. If we go to the numerator, it will become 10 to the power 5. Okay. Now you can see this. We are getting the t, it is equal to 2.303 into 10 to the power 5 into log 100 by 80. 0, 0 gets cancelled. Okay. So 2 4s are 8, 2 5s are 10. So you will get the value as 5 by 4. Now 5 by 4, if we will divide, we will get the value 1.25. Log value of 1.25 is here 0.0970, isn't it? So now we are rearranging these values. That is t equal to 2.303 into 0.0970 into 10 to the power 5. Then if we are multiplying these both values, we are getting 0.223391 into 10 to the power 5. So now what we are doing, if we are bringing this point towards one unit, this side, so it will become what? 4. Okay. Then it will bring this side, it will become 3. It will bring the point this side, it will become 2. It will bring the point this side, it will become 1. It will bring the point this side, it will be dissolved. So we are getting here t equal to 22339.1 seconds. Now we'll see girls' third problem. The half-life period of a first order reaction is 60 minutes. Calculate the time required for 87.5% completion of the reaction. So the given data is T half. Its value is given as 60 minutes. Determination of rate constant for half-life period is, we are using this formula. K is equal to 0.693 by T half. Now in place of T half, we are writing its value as 60. Okay, if we will divide this, we will get 0.01155 per minute. It is the value of K. Now the time required for 87.5% completion is, A value here is 100, X value is 87.5, and the K value is, just now we got the value of K, that is 0.01155 per minute. Now substituting the above values in the first order rate equation. As we know, this is the first order rate equation, isn't it? Now in this we are rearranging this equation because we don't know the value of t, that we are bringing to the another side. Okay, then this k will go to the denominator. This formula we are getting. Now we are substituting the values. In place of k we are writing the value of k as 0.01155. In place of a we are writing 100. Okay, above also in place of a we are writing 100 minus x value is 87.5. If you are subtracting 100 minus 87.5, we'll get the value as 12.5. Okay. So now here in this case, we are dividing this. That is 100 by 12.5. We'll get the value as 8. Here we'll get the value 8. Now the log. Here in the next step, what we are doing, we are dividing this value. So we will get 199.39 log 8. It is as it is. Okay, now we are seeing the value of log 8. Its value is 0.9. Now we are multiplying these both values, so we will get the t value as 179.451 minute. Next problem we'll see, girls. That is our fourth problem. At 30 degrees centigrade, 5 ml of ethyl acetate is mixed with 100 ml of 0.1 NaCl. The ester hydrolysis is studied by titrating 5 ml of the reaction mixture at regular interval of time against standard sodium hydroxide solution. The following results are obtained. Show that the reaction is of first order. Here you can see the table. Time in minutes, we are taking 0. For 0 minute, our sodium hydroxide volume is 9.62. 75 minutes, volume of NaOH is 12.1. For 190 minutes, volume is 13.1. For 183 minutes, volume of NaOH is 14.75. And at infinite time, the volume of sodium hydroxide is 21.05. So here we'll see the solution. The first order rate equation, we all know that it is k equal to 2.303 by t log a by a minus x. The acetic acid is formed in the reaction, is titrated with sodium hydroxide, and its concentration is determined. Look here, a minus x, it is proportional to V infinity minus Vt. That is volume at infinity minus volume at the time t. Then A, it is directly proportional to V infinity minus V0, means the volume at 0 time. Here, K, as we are using this formula now, that is K, it is equal to 2.303 by T log V infinity minus V0. Okay, that will be divided by V infinity minus Vt. So here in place of A, we are writing the value of A as V infinity minus V0. Okay, and in place of B, that is in place of A minus X over here, in the denominator, we are writing this value as V infinity minus Vt. So here V infinity, you have to see the table, girls. V infinity, volume at infinity, it is given as 21.05. Then minus volume at 0 time, how much? 0, that is 9.62. See here. Volume at infinity, volume is 21.05, and volume at 0 time 9.62. So we are subtracting these values, so you will get the value as 11.43. Now at the time 75 minute. Okay, at the time 75 minutes, volume at infinity, it is equal to 21.05, we know that, minus volume at the time. Here we are taking the time as 75, isn't it? So at 75 minutes, the volume of sodium hydroxide is 12.10. You can see the table. See here. At the time 75 minutes, the volume is 12.1. So we are taking that. If we are subtracting this value, so we will get 8.95. Now we are substituting this value in this particular formula. K it is equal to 2.303 divided by T. In place of T, the time here we are taking how much? 75. So we are writing here 75 into log, that is V infinity minus V naught. How much you are getting the value? 11.43. That we are writing, divided by V infinity minus Vt, that is time at 75 minutes. Its value is 8.95. So if we are dividing these both values, so we will get 1.277. That is log 1.277. Now in the next step, we are dividing this value, guys. That is 2.303 divided by 75. We will get 0.030 into log of 1.277 is 0.106. Now we are multiplying these both values, so we will get the K value as 0.00325 per minute. Next is here, we are seeing the time at, that is here the time we are taking 119 minutes. So the volume at infinity minus volume at the time. Time at which time we are taking the volume? At 119, isn't it? What will be the volume that we are writing? So at the time 119, the volume of NaOH is 13.10, isn't it? So if we are subtracting these values, you will get 7.95. Now, as we are taking this particular formula, in place of T here, we are writing the time as 190, isn't it? Then log V infinity minus V naught, its value is 11.43 divided by V infinity minus Vt at the time 119, that is its value is 7.95. Now we are dividing this. 11.43 divided by 7.95, we will get the value 1.43. Now we are dividing this. 2.303 divided by 119, you will get the value as 0.019. It should be multiplied with log of 1.43 is 0.155. We are multiplying these both values, so we will get the K value as 0.00325 per minute. Now we'll see about the time at 183. Okay, at T equal to 183. So here V infinity minus Vt, volume at the time T is here. See, V infinity value is constant. We all know that that is 21.05 minus V infinity at the time 183. How much the volume at the time 183? That is 14.75. See the table. So, and when we are subtracting this value, so you will get 6.30. Now we are substituting these values in this particular formula. So in place of T, we are writing the time as 183. At this time we are saying, isn't it? Now V infinity minus V naught value is 11.43 divided by V infinity minus Vt, that is at the time how much? 183. You will get the value as 6.30. Now first of all, we are dividing this value. That is 2.303 divided by 183. We will get the value as 0.012 log. Then we are dividing these values. 11.43 divided by 6.30. So we will get the value as 1.814. Okay, log value. Now the log of 1.814 is 0.26. We are multiplying these both values. That is 0.012 into 0.26. So we will get the value of K as 0.00325 per minute. So the K values are constant. You can see here the K values in this, but if the time is 183, the K value is 0.00325 per minute. If the time is 119, the K value is the same, isn't it? 0.00325 per minute. See, in the previous case, If the time is 75, at that time also you will get the k value as 0.00325 per minute. So here the k values are constant, isn't it? So therefore, this is first order reaction. Now we'll see the fifth problem, girls. The optical rotation of sucrose is 0.5 N Pascal at 308 Kelvin and at various time intervals are given below. Find out the order of reaction. Here also we don't know the order of reaction. We are going to find out the order of reaction. See this table. Time in minute 0. At 0 minute rotation is how much? Plus 32.4. Okay, optical rotation. At 10 minutes optical rotation is plus 28.8. 20 minutes optical rotation is plus 25.5. At 40 minutes optical rotation value is plus 19.6, and at infinite time the optical rotation value is minus 11.1. Now you can see the solution. The initial concentration A, it is directly proportional to optical rotation at 0 time minus optical rotation at infinity. And A minus X, it is proportional to optical rotation at the time t minus optical rotation at the infinity. Okay. So A, it is equal to what? R naught minus R infinity. So here R naught, that is rotation at the time 0. How much? 32.4. That we are writing. Then minus, this minus we are keeping. Rotation at infinite time. How much? Minus 11.1. So we are writing this. So minus into minus, it will become plus. And we are adding this 11.1 in 32.4. So we will get plus 43.5. Now we'll see at time t. Okay, time it is equal to 10 minutes. Then RT, rotation at the time t, that is at the 10 minutes, how much? 28.8. Now RT minus R infinity. RT value is rotation at the time t 10 minutes is 28.8 minus then rotation at the time infinity. Infinite time is 11 minus 11.1. Minus into minus again plus. We are adding both the values, so you will get 39.9. Then look at this formula. K it is equal to 2.303 by T log this value R naught minus R infinity divided by RT minus R infinity, isn't it? In case of T here we are keeping the value of T is time is 10 minutes, here we are taking log R naught minus R infinity value. Just now we got how much? That is 43.5 divided by RT minus. RT means at the time 10 minute. We are getting the value as RT minus R the infinity, its value we got just now, that is 39.9, isn't it? We are dividing these values, that is 2.303 by 10, we'll get the value as 0.2303 into log this values we are dividing, so we will get 1.090. Next step, we are taking the log of 1.090, that is 0.037. We are multiplying these both values, so you will get the value of k as 0.00862 per minute. Next is, we are taking the time 10. No, here the 10 is already over. Here we are taking the time 20 minutes, isn't it? At 20 minutes, rotation is, optical rotation value is how much? 25.5. You have to see the table, girls. Then you will understand very easily. So here, RT minus R infinity. So the rotation at the time 20, its value is 25.5 minus rotation at infinity value, that is the constant value, isn't it? We know, but that is minus 11.1. Minus into minus will become positive plus. So we are adding both the values, so we will get 36.6. Here we are using this formula k equal to 2.303 by t log R naught minus R infinity divided by RT minus R infinity. Now we are keeping the value t. T is how much? 20. So we are writing here 20 log R naught minus R infinity. Just now we got the value. Means in the previous case we got the value as 43.5, isn't it? That we are writing divided by R t minus R infinity value. Just now we got, that is 36.6, isn't it? Now we are dividing this 2.303 by 20, you will get the value as 0.1151 into log. We are dividing this value, so we will get 1.1885. So the log of 1.1885 is 0.074. Now we are multiplying these both values. We are getting the value of k again as 0.0086 per minute. Next is at the time equal to 40. So rotation at the time 40 is, its value is 19.6. It is there in the table, girls. You have to see the table. Now our rotation at the time 40 minus rotation at infinity, that is 19.6 minus, then minus rotation at infinity is minus 11.1, isn't it? Minus into minus plus, we are adding both the values, so you will get how much? 30.7. Now we are using this formula again. In that, in place of t, we are writing that value of t as 40, then log r0 minus r infinity, that is rotation at 0 minus rotation at infinity. We got this value in the previous case, 43.5, that we are keeping, and divided by rt minus r infinity. Just now we got the value as 30.7. So now we are dividing these both values, so we will get log 1.416. Now we are dividing these values, that is 2.303 by 40, will get the value as 0.057. Now we are multiplying these both values. Again you can see we are getting the k value as 0.0086 per minute. Here also at time 10 minutes, at time 20 minutes, at the time 40 minutes, for all those times as we are using, we are getting the value of k as constant. How much we are getting? 0.0086 per minute. Hence, we can say that this is the first order reaction. Thank you for listening my lecture, girls.